Alright, how's it going?
Pie day.
Pie day. Where's the pie?
I thought you were supposed to bring it.
Oh no.
The cupcakes, the pie, the...
I'm not vegan anymore, so I can eat pie today. It's awesome. Very excited.
The evaluations, those are for nothing then?
Yeah. So, questions. I can read through the study guide, which you've probably already read through, but if you got questions, that would be more useful to you probably. I'm still grading PA5. It's going to take me another day or two. But the most common things I'm seeing, and these are really minor issues, it's a few points, but the most common issues I'm seeing are, one, not noticing if there's a problem in the knapsack file, like not checking to see if you actually scanned integers. And for some reason, a lot of code is blowing up if the lightest item in the bag has a weight more than 1. I'm getting weird answers. In one case, I got like 2 pages of like large negative numbers, and so there's some initialization that's popping up in an edge case, but those are a few points each, so it's not like a super big deal.
It's kind of unrelated question. How do you pass a command line argument into GDB? I forgot how to do that.
You can say run space and put commands arguments after it in GDB, and that seems to work. I didn't think it did, but it seems to be working. If not, there's weird things you can do where you like duplicate what's hard to do is redirect standard in. That I've got notes written down. You'd have to like duplicate the type and stuff like that. But if you just want to run with a command inside GDB, say run space and then put in your command line arguments, and it picks them up from there. Well, we can just run through this. Exam itself, so there's 10 questions. You don't get a choice which questions to do. Well, you always have a choice, but there's only 10 questions on there. So 4 of them are full-on programming questions. One of them is writing a few lines of code, so it's like 4 or 5 programming questions. There's no short answer, fill in the blank, remember some obscure definition kind of things. So the other 5 questions are like the things you've done on the board. So balancing a tree, heapifying a heap-shaped collection of numbers, adding something to a heap, deleting from a heap, doing rotations, deleting things, stuff like that. Hashing things and figuring out where they go in a hash table, stuff you've done on the board. So half the exam is that, half the exam is programming. Most of the program questions will be fairly short, similar to things that you've done, but possibly in a more general context. I got one programming question that's going to be somewhat challenging, I suspect, but it's 10 points like all the other questions, so you should be able to get at least a bunch of those points. Yeah?
Sorry, I think you probably already mentioned this, but what day is the time?
Good question. So there's an exam on Monday at 10 and then on Wednesday at 11. And you're welcome to come to either one, not both, not neither, an exclusive order. It's probably going to be crowded on Monday if past data means anything, so I'll be pulling in extra chairs and I'll probably clear off this table and make space for people. So if you want a relaxed environment, you could do it on Wednesday. Yeah?
So the balance trees, do we write code or just the...
So I'm not going to ask you to write code for balanced trees, but you might see a tree and you might need to figure out what the balance factor is at each point, right? So height of the left subtree minus height of the right subtree, and you might need to figure out if something is unbalanced, and if it is, what kind of rotation or rotations do you have to do, and then actually perform those rotations. But not writing code to do that.
Good. And how about PA5? Do we have PA5 in Spinal?
Like
Snap, just problem, something like that.
yeah, so you should definitely know everything that you needed to know for PA5. So algorithm for a knapsack problem, or if I give you something similar like rod cutting, or something where I describe the recursive approach to solving it, right? You should be able to work with code, modify code, write code, analyze code, that kind of stuff. Do you have your hand up?
It's
You got time. All right, so is that clear about like structure of the exam? So 110 minutes, the usual 8 pages of notes, etc., etc. All right, so so what have we been doing this quarter? So obviously structures, the beginning of this is largely the same as we talked about for the midterm. So structures, right? The structure statement, declaring a structure. If you like type defs, you can use type defs on your exam to save some typing, but be careful when you try to use type defs inside size of. So mostly we have pointers to structures. So struct, structure name, star, variable, right? Should know how to use Malloc. And in particular, we usually Malloc memory for structures, unless we're just defining a structure or an array of structures. And how you access the fields of a structure, you use a period or you use an arrow if it's a pointer, right? Arrays of structures work like any other array. Yeah?
Are there any topics that people usually miss on this final?
I've never given this final before, so I don't know. No, not usually. I mean, it's pretty rare. I mean, occasionally a student will be like, "Oh, I totally forgot to study C," But it's pretty rare that I don't think I've ever had a case where everybody was like, "Oh, I didn't know we were going to have to know such and such," right? Because I write this after I've already sort of got the final pretty much in mind. So, but there's a lot on here. There's a lot of like broad brush strokes. So linked lists, obviously we've spent a lot of time on linked lists. I'm not going to ask you to do linked lists as an array, okay? Like PA1, we don't do that. And if you feel like you want to do your linked list problem with an array, fight that urge, okay? When you do linked lists, you should be thinking, here's a structure, there's a data piece, and there's a pointer to another node, right? So don't implement it with an array and my null -1 and all that stuff. That was just an exercise. So linked lists, right? Linked lists might have sentinel nodes, they might not have sentinel nodes. Bless you. Right, if there's a sentinel, all it means is the first node of the linked list isn't actually part of your data. It's just a node that's always there. We never search it, we never delete it, we never modify it other than what it points to. Right, it's just a holding place for the pointer to the actual first node of your list. If there's no sentinel, then an empty list is null. And a non-empty list has exactly one node. And a list with 2 things in it has exactly 2 nodes. If there's a sentinel, an empty list has just the sentinel. A node with 1 piece of data has a sentinel and a data node, and so on and so forth. So we've searched, we've traversed, insert, delete, all of those things, right? And again, what you want to strive for in preparing for this is understanding the concepts and the algorithms, not the code, right? So it's not bad to go through your code, especially if there were things that you kind of struggled with and you want to refresh yourself on those. But make sure you know, here's a node pointing to a node, and I want to insert something in between. What do I have to do? Right, I have to create a new node, and I have to have the one that comes before it point to that new node, and the new node has to point where that old node pointed, and then figure out how you would write code to do those things. Right, but concentrate on the algorithms themselves. And that's true for pretty much all of this. Doubly linked lists, we didn't play with those, but the concept is, just having a pair of pointers, and some people did this anyway because it kind of simplifies your life. So we just have these back pointers. And so if you insert, you got a little more work to do. So let's say this is A and this is B and this is new. So what happens when we insert, right, n equals Malloc? So that gets you a new node. And we need n to point to B. And we need n to point back to A. So that points there and that points there. And then A needs to point forward to N. So that changes that. And then B needs to point backwards to N. All right, and now you've got N sandwiched in between A and B. And, this was easy to write because I had something called A, the node before, something called B, the node after, and something called N, the node I'm trying to insert. If I didn't have this, I'd be doing things like A arrow next arrow previous equals N, or N arrow next equals A arrow next. And that's where you get into trouble with order sometimes. Because if I do this as A arrow next after I've changed A arrow next, right, I've got problems. So you can always save yourself some trouble by, before you start changing anything, just make some temporary variables, right? And draw a picture and label them, and it helps get your code right the first time, which is kind of what you got to do on a test, because you don't have a compiler to check it out with. So that's kind of a general trick. Order of complexity. So I'm not going to grill you on order of complexity, but I'd like you to take away from here some fundamentals. So order n means if you have n pieces of data, you got to do roughly n things to process it. Okay, so what's the quintessential search example that's order n?
Searching through n amount of data for one piece of
Yeah,
data.
just searching through n pieces of data without any kind of fancy structure, any kind of order. Typical case would be an array of just unsorted numbers. And you're searching for some number. You basically got to check every single thing in your collection to know if your number's in there or not. And so that's order n, unordered search. If you're ordered, right, you can do log n. That's playing high-low. So check the number in the middle and then go halfway above and below and keep dividing in half until you find your number or you run out of possible numbers to check. That's log n. And so in a linked list, right, if we're searching for something, that's an order n. Because it's kind of like an array, but we can't jump into the middle. Even if these things are sorted, you got to start at the beginning and just check each item. So that's kind of order n. If you know that you want to insert something before this node, that's an order 1. Right? All you got to do is make a new node and have this, let's say you want to insert after this thing. I make a new node and I just have this thing point to that and have this point what came after. Oh, thanks. So linked list, and let's say you want to insert after this node, right? Make a new node, point where B is pointing, have B point to that. This is like 3 instructions. And it doesn't matter that there's a million things before here and a million things after here. As long as you know that you want to insert right after this, it's order 1, right? But finding this node, that's order n, because you got to start at the beginning, and if this is the millionth node, it's going to take you a million steps to get there. So you don't need to memorize these orders, right? And in fact, that's kind of futile to try to do, because there's like best case, average case, worst case, and so on and so forth. But just kind of have an understanding what we mean by these orders of complexity.
So if you're also on the exam, would you say something like, you know, if you were to insert into a linked list, then what order is that?
Yeah, yeah. Or if you're searching an array of unsorted numbers, what's the order of that? Or which of these has a better search order, searching a linked list or searching a binary search tree? There's a hint in there. All right. So the star and ampersand, I think people are actually really comfortable with that now. I don't know, are you? I mean, you've been doing this, and it's probably like horrifyingly bizarre the first time you encountered it. I know it was for me. But star says the thing pointed to by something, ampersand says the address of something. Right, so it's just two dereferencing and referencing. And then when you have a structure, right, if var is a struct my struct and it's got a field named field, you can say var dot field to get that field. If it's if you have a pointer to a structure, then it's thing pointed to by the pointer dot field, and that's what we write as this. So you can think of the arrow as dereferencing a pointer. So whatever it points to, give me the field of that thing. Pass by value, pass by reference, I already said there's no short answer multiple choice on here, so I'm not going to be able to ask you about that. But, you know, pass by value says we pass the value of an argument, right? So a function gets a copy of whatever argument you pass to it, and that's what C does. It's always pass by value. Pass by reference means if I call a function and I say function parentheses x, the compiler actually passes the address of x. So call by reference, it's kind of always putting an ampersand in front, and other languages do that, but not C. C, if I say function of x, right, it actually passes the number 7 to the function. Nothing to do with x. Right, it reads x to figure out what the value is, but whatever that value is, that's what it passes. It just takes the number 7 and it throws it on the stack, and it says, here's your argument, it's a 7. Right, which is why in my function, if I say x equals 12, it has nothing to do with this x, right? Because I didn't pass x, I passed a number 7. So that's pass by value, that's all that C does. And if I happen to say function ampersand x, right, so here's my memory, and down here at location 100, that's where x is stored, right, and there's a 7 there. If I do this, it says function 100. Okay, it passes the number 100, which is the location where x is stored in memory. Again, nothing to do with x, unless my function says, hey, let's go to that location and change what's stored there, right? now my function knows something and it's doing that to change the actual value of x. But I can't change that 100. Yeah?
So would it be like a correct way to think about it by thinking pass by value, like localizes variable, just pass by reference normal?
Effectively, yeah. Yeah, that's a good way to think of it. So the argument to a function in C is always a local variable. And if it's passed by reference, then it's a little more like a global. All right, Malloc, free, Valgrind, right? Malloc allocates memory, free frees memory. You've been doing this all quarter. There's not a whole lot else to say on there. And Valgrind you use to help you figure out if there's things going wrong. GDB you've been using. How many people here use GDB fairly regularly now? That's good.
Are you gonna ask about watch points on that? Because outside of the quiz that we did in class, I've never been able to get a watch point to work correctly.
Watch points are a little quirky sometimes. But the theory is you just say watch space variable name, and they work.
It's a good theory.
It's a nice theory. I don't know. Let's play with. No, they're not going to be watch points on the exam. Let's see. No, I'm gonna make my life easy here. Fair enough. So I goes from 0 to 10, and if I squared is bigger than 50, we're going to increment j. And let's see if we can get it to hit a breakpoint when j changes value. And if this doesn't work, then we'll have like National I Hate Watch Point Day. Alright, so I'm going to say start. I'm going to say watch j. And I'm going to say continue. And so it's telling me the old value of j is 0, the new value is 1. And if I look at the value of I, it's 8. Right, so when I was 7, 7 squared was less than 50, so this is the first time it's bigger than 50. So that kind of works. But
I look at the issue where like it's a smaller function that gets iterated in that like bigger program. It's all like
so
break at the point and then watch in the program and then
right.
continue.
So you gotta specify the function that you want to watch in. I don't remember how to do that, but I will find out and I'll let you know. But yeah, you've got to specify the context if it's not a global or if it's not in your main program.
I tried to like figure out how to do that and looked at a bunch of flags and tried a bunch of different things, but the end result was I would always say watch this variable once I was in that smaller function and be like, yeah, no, this is good. And then I'd hit continue and be like, there's no variable to watch.
Yeah. And Woohoo. Okay, so why am I seg faulting?
Did you declare function?
I didn't prototype it, and I think that's freaking it out. Because if it doesn't know that it's supposed to have an argument, it's probably assuming there's no arguments, and when I push something on the stack, it's possibly freaking out. But let's see. Oh,
Your function returns a number, right? So
yeah.
would that cause any problems?
It should be okay.
Oh, it doesn't return anything for an end.
That could be a problem. Well, but I never actually return these. Oh, never mind. I know what. I meant to do steps. So this was a long-winded way of saying something that might not even be very useful. But when you're running GDB and you're inside some function calls, you can do something called backtrace, and it will show you all of your calls and where you are. This might be useful when you're doing recursive programming. So I'm in what's called call frame 15, was line 10, and that called function with n equals 10, and that called function with n equals 6, and so on and so forth. And you can see what your current frame is, and you can change call frames and then look at the values of variables in other functions and so on and so forth. And so that's one way you can set up watch points in a function, is put a breakpoint at the start of the function, turn on your watch, and then continue.
I don't know if this is true or not, but I was reading something talking about doing recursive functions. All the manipulating of the stack really slows down the program, and you can get like a 50% decrease in performance by doing recursive functions.
It depends how much of your function is recursive calls versus other stuff.
Yeah.
Like if you had 1,000,000 lines and then a recursive call, well, it's not going to be 50%. But things like knapsack, where you're really, you do a couple of arithmetic operations and then you recurse, is definitely killing your performance.
Yeah.
Because every time you make a call, you've got to save not just where you were, the return address, but all of your local variables. And you've got to adjust the stack because your locals are stored on the stack, and so on and so forth. And it's typically a spendy operation. Although some processors, like the VAX, actually had a single machine language instruction for doing all of that process switch when you make a call, specifically for efficiency. All right, so that's a little far field, but you're not asking other questions, so I'm just kind of going for it. All right, so GDB. You go with GDB. Make files. I would like you to know how to make honest make file. Okay, not just a 1 or 2 liner that says gcc-o file everything.c, right? But how to compile .c's into .o's with a -c switch, and then link the .o's together with a GCC. Okay, and a lot of people already know how to do that. But if you don't, go back and review that. Yeah.
Would you like to? Oh, you want us to know that, but is it going to be on the?
It could be.
Sounds
I
good.
could give you a make file and ask you to, now you're going to add this new function to your project, modify the make file to. Yeah, that is a good one. Abstract data types, this is just the idea of if we don't pay attention to the implementation of a data structure, what does it look like to us? So for a list, you want to initialize, you want to search, you want to insert, maybe you want to free all the memory associated with the list to delete it, and so on and so forth. For a stack, we can push, we can pop, we can see if it's full, we can see if it's empty, right? And that's the abstract view of a stack. The implementation view of a stack is, here's an array, and here's a variable called sp, and we increment when we push. or here's a linked list, and when we pop, we take the thing at the beginning of the list and we delete it, and so on and so forth. So just knowing this distinction, and that's going to come up a lot in 223, because a lot of the data types we'll use in 223 are already built for us, so we'll be coming at them abstractly. So just concept there. I would like you to know recursion. Surprise. Recursion and recursive algorithms programming. So recursive algorithms are things like here's a recursive algorithm for finding n factorial. If n is 1, n factorial is just 1. If n is bigger than 1, n factorial is n times n minus 1 factorial. Right? And we know that if we think about what a factorial is, from that algorithm we can write code. Right? And the code would be, you know, factorial n, if n equals 1, return 1, return n times factorial n minus 1. Kind of comes straight out of that. But lots of things we can think of recursively. For example, the height of a tree. Right? Now we've said the height of a tree is the number of steps from the root to the deepest leaf. But that's not typically how we write a height function. We take that definition of height and we come up with a recursive version of it, which says the height of a tree is 1 plus the height of the deepest subtree, either on the left or the right. And now we're never like counting links from the root to a leaf node. We're never looking for leaf nodes. We're never doing a traversal. We're just saying return 1 plus the largest of height of tree dot left, height of tree dot right. Right? But with an edge case saying if the tree is null, return minus 1. So that's like height of t equals minus 1 if t is null, or 1 plus the maximum of height of t left, height of t right. So what would it look like if we tried to write our own version of string length? At least one person did this on PA5 because they said they forgot that there was a string length function. So if we just wanted to write my own version of string length just using a for loop, right? Do something like right, initialize L to 0 while SL is not the null terminator, increment L. And then return L. So that's like CSE 121 type code, right? It's easier than a palindrome program. So what if we wanted to write a recursive string length function? So what would be a recursive algorithm for determining the length of a string?
Would the smallest one return the null terminator and work backwards? Kind of like recursive.
A little higher level, just plain description. Here's a string. Hello. Recursive description. How would you figure out how many characters are in here?
Pretty similar to the height function, right? Instead of returning 1 plus the max, you would just return 1 plus the string length of the max.
Yes. So this takes some string. If string is empty, return 0. Otherwise, return 1 plus the string length of the address of the first character, right? So take a substring. Take the string starting with the second character and find the length of that string, and then add 1 to it. So that's the weird way of doing substrings, but it's a pseudocode algorithm, right? So length of a string is either 0 if the string's empty, or it's 1 plus the length of the substring starting with the second character. And so again, it's a 2-line program, no looping, it's using recursion. So that's the kind of thing I mean here when I'm talking about writing, thinking of iterative algorithms recursively, right? So tree height, string length, 2 examples. If you have a recursive definition, writing recursive code usually pretty straightforward. So tree balancing, right? So tree balancing, see if the heights are close. That's called the heights and the difference in an absolute value. And you want to know if the left subtree is balanced. So you just say, is the left subtree balanced? Balanced tree dot left. And then balanced tree dot right. Tree traversal, the way we do LNR traversal on a binary tree is first do LNR traversal on the left subtree, then print the root, then do LNR traversal on the right subtree. Right? It's fundamentally a recursive definition. But from that definition, you can write the 3 lines of code that get you LNR traversal. All right, good on that. Stacks and queues. So you've done queues a few times, right? Because you used them in PA4. So stacks, right? Push at the top, pop from the top, wherever the top is. Could be up here or down there. But push and pop, underflow is when you pop from an empty stack, overflow is when you push into a full stack. Right, so either not having anything in there or running out of space. And 2 main ways we talked about implementing them. One is with an array. And so you have a variable that says where's the top of the stack, which is either, you know, the last thing you pushed or the next thing you're going to push or something that tells you where the stack actually sits in your array. Or you can implement them with a list. And with a list, easiest way, just push it by adding in the beginning, pop by removing from the beginning. And then queues are a little trickier because we have 2 ends where things happen. We have one end that we put things into, we have a different end that we remove things from. Okay, but abstractly, queue is just a collection of things that you can add to in a particular order, and you can remove them in exactly the same order that you added them. Okay, but we usually think of a head and a tail, and we insert things at the tail and remove things from the head. I think I've been able to be consistent. I just have to do it for 2 more days. So we inserted the tail, removed from the head. And we can implement this with an array, but if we have an array, we need a pair of pointers telling us where to insert and where to remove. Or we can do this as a linked list. And the way we did the linked list when we did this in code was you insert, where did we insert it at the beginning or the end of the list?
I inserted it at the beginning and then just printed it in reverse.
Sneaky. You can do it either way for a queue. But, you know, make a linked list and your insert's going to go either in the beginning or the end, and then the remove is going to just take it from the other side. And it makes no difference. It'll still act like a queue, right, as an abstract data type. Doesn't make any difference to you whether I'm actually inserting here or there, right, as long as it's coming out in the same order that it went in. So stacks are LIFOs, last in, first out. Queues are FIFOs, first in, first out. And if you do an array, right, it's a circular array basically. So if you're putting things into your queue and you put something in here and that's the last element in the array, the next time you put something in, it's going to come back to the beginning of it, and it's like an array that's set up like that. And that's a useful structure for a lot of things. All right, hashing, we did hashing yesterday. So I don't need to go over that again. Well, collision management, the other way to handle collisions instead of probing and finding another place to store it, the other thing we can do sometimes is have each entry in your hash actually be the start of a linked list. And then if two things hash to the same location, you just put them side by side in a list. Maybe you alphabetize them or something. And so if I've got 5 things that all pointed to index 7, they'll all be in a linked list that's pointed to by index 7. Right, so that's something called chaining. All right, trees. So mostly we've worked with binary search trees. I don't think I mentioned red-black trees in here. So binary search tree, right? Basic property: everything on the left is smaller than the root, everything on the right is bigger than the root. So there's an order associated with it, and it's basically a linked list that we can do binary searches on. So we have pointers going to the middle of each side of every sublist. 3 depth first traversals: left node right, node left right, left right node. Right. Breadth first traversal, which moves across and slowly goes down, and to implement that we usually use a queue. We can search iteratively. We can start at the root and we can just follow the left-right directions until we either run out of nodes or we find what we're looking for, or we could do a recursive search. Right? Recursive search says if your number is bigger than the root, search the right subtree and tell me what you conclude. And if it's smaller than the root, search the left. If you don't want to do that, you could just say, how do I search for a number n? So search for n in the tree T. If T is null, return false, because you don't find n in a null tree. If T data equals n, return true. If I'm really lazy, I could just say return search T dot left n, or search T dot right n. So I'll just search both subtrees for n, and if either of them contains n, I'll return true. It's extra work because I know it can only be on one side or the other, but that would also give me a correct value. That one's way more expensive though. That's like an order n search algorithm. So inserting, same thing. We can travel down to a leaf and then tack our new node on either side, or we can say if tree's not null, insert into the left or right subtree and replace the right subtree or left subtree. So most of these things can be done recursively or iteratively. AVL trees, so those are balanced trees, so know how to calculate the balance factor of a node. Know when your tree is unbalanced by looking at the balance factors, right? So if you insert a node, recalculate the balance factors, work your way up. First time you find a 2 or minus 2, you know your tree is unbalanced. And at that point, you can do a rotation. Okay, so I strongly recommend that that you have a copy of that. Right? I should just give you that. You want me to give you this?
Yeah.
All right. I'll make a copy of this. I'll give it to you with your exam. All right. So yeah, know how to do those rotations. Red-black trees, the only thing I want you to know about red-black trees is that it's a way to do a balanced tree, but it's not perfect balance. It's balanced in the sense that the difference in heights is always within a factor of 2, as opposed to within a difference of 1, right? So 1,000, 2,000, that's still balanced as a red-black tree. I'm not going to ask you about characteristics of a red-black tree and properties of who can have what children and so on and so forth. Tries, you should know the basic concepts of a trie, right? It's a really wide node structure. If we're storing words, it would have a node for each letter. And it's also got this end of word or end of string field. And you take each letter of the thing you're storing and you follow a link. And if it points to null, then there's nothing coming off of that letter. You've got to create a new node. If it's not null, it's already pointing to another trie node, and so you just move down to that and you find a letter for the next piece of your input and so on. And when you get to the end of your string, you follow the last letter to another node. That's where you set the end of string flag. And you did this in class for a couple of days, so you should be good with that. So basic concepts, being able to work with pictures of a trie to analyze it or to make changes to it. If I gave you a structure that had 26 fields and an end of string, right, I might ask you to do something with that. That shouldn't be totally new to you. All right, so we'll talk about these last few things tomorrow. And things you should be prepared to do. There's no surprises there, but we'll talk about those. Bring questions, and if we finish all this tomorrow, I'll probably start talking a little bit about object-oriented programming. Just kind of a setup for spring.
Just when I can find